Alright, so welcome to this video. This is a supplementary lecture for our class in dynamics. Today we'll have a review on the topic on the vectors, and then we'll extend this topic to the vector value functions. So vector is basically a directed straight line. So for example, we have this 3D space. So we have x, y, and z, and then it's a directed straight line. So for example, this first point and then the second point. So our vector would be a directed straight line from point, let's say point A, or let's say point 1 to point 2. Okay, so this will be our vectors. So we also discussed that vectors basically have a magnitude. So the characteristic of a vector is that they have magnitude and direction. Okay, so meaning it's a different vector if it's from point 1 to 2, and then a different vector would be if it's from point 2 to point 1. Okay, so let's say this is a vector A and then this is a vector B, so it's different. Okay, we also discussed the different operations of vectors. Like for example, we talk about the addition of vectors. Alright, so let's say addition of vectors. Okay, so for example, we have a vector A. So I'll just do this graphically for now. Okay, let's say we have a vector A, and then we have to add that to vector B in this orientation. Let's say this is the vector B, right? A vector A and then vector B. So if we want to add them up together, so basically what we did is just this is the vector A and then the vector B. Right. Okay, so the length of or the magnitude of the vector would be from this initial point to the final point. So this is our vector sum. So A plus vector B. So this is the vector. Okay, so we also have actually, if we have two vectors and then if we want to sum it up, then we have two methods. We discussed the what we call as methods is the parallelogram rule, and then the triangular rule. So basically the parallelogram rule is just we're making a parallelogram, from the two vectors. For example, this is our vector A and then this is our vector B. So we're actually something like tracing or forming a parallelogram. So this is your B, and then there's something like a mirror image. Then this one also, there should be a parallel mirror image. Okay, and then from this point to the final point, then that's the hypotenuse. So we can use that. We can find that from this formation. Okay, for the triangular rule, actually we're just dealing with the inside angles. Sorry. Okay, so we're dealing with the inside angles. So if we know, like for example, we have this angles here, angles. So basically we are using the trigonometric rules or identities to solve those, the values of the sides. So that's what triangular rule is. Right, so next we also discussed multiplication of a vector and a scalar. So scalar multiplied to, okay, that's not a cross product, right? I repeat, that's not a cross product, it's just multiplication. So scalar times a vector. So for example, this is your vector AE. So vector AE, you try to multiply it by magnitude, or let's say just a scalar value. So let's say the scalar value is 2. So if you multiply that, what you get is just 2a. So we see that the length, this length is just multiplied twice, but the direction is just the same. Okay, so that's just it. Okay, and then last time we also discussed on the dot products. Okay, vector products. These are, let's call it dot products. Okay, so dot products, basically, if we have this vector, let's say vector A, and then we multiply by another vector. Let's say another vector is this. So the vector product, or the vector product or dot product, A, okay, dot B, A dot B, is just simply the product, or the sum of the products of their components. So recall that for any vector, we can represent that in a Cartesian form. Let's say this vector, so we have this ax I plus ay, okay, j along the j direction, then az along the k direction. Okay, so that's the Cartesian representation of a vector. So it has 3 components if it's in 3-dimensional space, or just 2 components without this if it's just a 2-dimensional plane. Okay, so the same also with the vector b. We have this bx along the I direction plus by along the j direction, and the bz along the k direction. Alright, so it's actually ax bx plus, so take note, this is the magnitude only of the vector A, then the x component of the vector b. Okay, ay plus by plus az plus times bz. Oops, alright, sorry. Alright. Alright, here it is. Sorry. Okay, next is we can also use this dot product to solve for the angle between. For example, this is the angle we want to find, so we can solve that. It's just the same. A dot B is just the magnitude of, the product, the magnitude of AB times the cosine. Let's say the angle is theta, so cosine theta. Okay, so how do we solve these A and B values? Take note, this is just a scalar magnitude. Right, so scalar magnitude is just for A, we can write it as ax squared plus ay. Right, ay squared plus az squared. The same goes true with this b, so we have the square root of bx squared plus by squared plus bc squared. Okay, so the dot product is sometimes referred to as this scalar product. Okay, scalar product simply because if you multiply these two vectors, what you get is a scalar. Okay, so that's it. Another operation we discussed last time is the cross product. Okay, a cross product, okay, let's say letter D, so a cross product. So this is actually a multiplication between two vectors. So the difference between the cross product and the dot product is that the cross product is, if you multiply, the two vectors, the product is a vector, whereas in the dot product, if you multiply that, what you get is a scalar product. What you get is a scalar quantity. Okay, so let's say we have these two vectors. Okay, vector A and then vector B. Let's draw this in 3D. Let's say vector D, B. So let's see. Okay, so let's say this is our x, this is our y, and then this is our z-axis. Okay, so two vectors, we multiply that. So what you get is, if we A cross B, this actually becomes something like a matrices. So I, in terms of J, K, and then this is the AX, AY, AZ, and then BX, BY, BZ. Alright, so what we get is a vector that is out of plane. So this is the plane actually before. So it's something like this. This is the plane, the XY plane, right? Let's say XY plane. So what we get if we cross product A and B is that we get a vector that is out of plane. So this is A cross B. Okay, and that vector is perpendicular to B and then perpendicular to A. Okay, so how do we solve this value? Is just something like, we can get the component of I by, like for example, we want to solve for I, then actually something like that one. So we'll start with AY. So AY times multiply to BZ, and then so let's try it. So AY BZ minus AZ times BY. So something like that. So AZ times BY, that's along the I direction. Okay, and then if with J, so if we try to solve for the J component, then it's just something like this. Okay, I J K, so AX AY AZ, then BX BY BZ. Okay, so let's solve for J for example. Okay, so actually we're not considering this, so we'll start with AX and then multiply by BZ and then minus the AZ times the BX. Okay, so let's write it here. So for the J component, okay, so take note, just for the J component, I guess this is something like a simplified procedure. Let's put, it is required that we have to make a negative sign here outside. All right, here's the negative sign. So AX times BZ minus AZ times BX. Okay, so that's the J component. Okay, another one is, let's solve for the K component. So it's just the same. Right, so let's see. For the K component, I, J, K. So we have this AX, AY, AZ, and then BX, BY, BZ. Right, so let's solve for k. Let's cross this out, and then what's left is we'll start with ax multiplied with by, then minus this ay times bx. Right, so ax by minus ay bx. Right, so that's the component of the vector here. So if you sum this up here, then that's gonna be the Cartesian notation for this vector. Okay, so next, actually, what I wanted for this video is this topic. Okay, the vector value functions. Okay, let's discuss this vector. Okay, let's say it's different vector valued functions. Okay, so vector value functions are vector value functions are of the form, let's say our vector is r, it's a function of time, say, so we have this function f of x in the I direction, so plus f of, no, let's not use f of y, maybe no, not f of x, sorry, f of t is a function of t, then g of, let's say g of, yeah, let's rewrite it. Okay, so this is our function, vector value function. So vector r, so as a function of time. So we have this f as a function of time in the I direction, right? So I'm trying to make it bold, and then along the j direction there's another function, let's say g of t in the j direction, and then in the k direction there's another function, so let's say h of t along the k direction. Alright, so basically the difference last time, the vectors that we have considered is, all these coefficients here, they're just constants, but right now they're not constant anymore. They're functions of time, so they can be linear functions, like sine functions, whatever. Okay, so why I introduced it here, or why I included it here in our subject in dynamics, is simply because we can get an intuition for the vectors, accelerations, all those parameters in mechanics, in dynamics. So basically what this is that we can determine a curve, the path where that point traces, let's say for example at time 0, or at time 1, at time 2, at time 3. So we can trace a path of that particle or point. Okay, so let's take for example, right, so let's take for example, we have this r as a function of time. Okay, so this is our vector. Alright, so we have this 2 minus 4t in the I direction, plus -1 plus 3t along the j direction, okay, plus 3 plus 2t indicated in the k direction. Okay, so if you want to, as I mentioned, that if we, let's say, substitute the value of, like, for example, time is equal to 0, then what will be the resulting vectors, or the graph let's say the illustration of this vector r. It's actually the position vector. Okay, position vector. Okay, so let's include an interval. So what we need is we have to include an interval of time. Like for example, if we want to trace the path that the position is tracing, then we have to define the interval. Let's say we have this from time 0 to time, let's say 1. Alright, so let's try to break them down. So let's substitute what would be the position in x, x, y, or z if time is equal to 0. And so time is equal to 0. So the position is, or let's say r of 0. So basically 2 minus 4 times 0. So this is along the I direction, plus minus 1 plus 3 times 0. So the j direction, and then plus 3 plus 2 times 0 along the k direction. Okay, so if we simplify, this is 0, this is 0, 0. Alright, so I'll simplify, we get a 2i minus 1j plus 3k. Okay, so this is actually the position of the vector r at time 0. Okay, and then later on we'll trace that. Then let's try at time is equal to 1, what would be the position, of the vector. So that's why actually this is a position vector. Right, so let's substitute all the t's by 1. Right, so 2 minus 4 times 1 along the I direction, plus minus 1 plus 3 times 1 along the j direction, plus 3 plus 2 times 1 along the k direction. Alright, so let's simplify. So 2 minus 4, it's actually minus 2i. Okay, what's this? Plus, 3 minus 1, so this is 2j. Plus, what's this? 3 plus 5. So it's actually, 3 plus 2, so it's actually 5k. Okay, so this is the position at time is equal to 1, and then at time is equal to 0. This is the position. Right, so let's try to draw, or let's try to plot. So let's say, for example, we have this, right? Let's say this is x. Alright, so let's say this is x, this is y, and then this is z. Right, so for our first vector, which is r0, so we have 2i along the x direction. So let's say 1, 2, and then a negative j. So this is the positive x direction, positive y, and then positive z. So if it's negative, then it's actually the opposite direction. So along here we have this negative, and then plus 3k 3 along the z direction. Okay, so if we want to trace, so it's basically like this: 1, 2, 3. Okay, so let's draw. Alright, so I'll try to draw. Alright, so this is the point. So the position vector is at this point from the origin. So this point is 2, -1, and then 3. Alright, next let's draw the graph of vector r at time equal to 1. And so we have a negative 2 along the x direction, so this is the positive x. So if you want the negative, then it's just in the opposite side. Okay, and then positive 2 along the j direction, so we have this, let's say 1 2, and then positive 5 along the k directions. Okay, so basically here 1 2 3 4 5. Okay, and then we'll draw parallel lines. Okay, what's this? Alright, so this is it. So this is the position. Okay, so the vector from this origin is this one. Okay, so this is r of 1, and then this is 1 is r of 0. Right, so the point is negative 2 2 and 5. So basically what we're doing here for this, the parametric form or the vector valued functions, is that we can trace the position of this point. Okay, so in this case we have just like something like a straight line, because this is a linear function. So let's say, for example, at t is equal to 0.5, then maybe it's here, and maybe it's here, or if t is equal to 2, maybe it's here. So actually this is the path with the curve, right? So let's just label it. This is actually the curve that it traces. So the important thing is that or how is it related to our subject in dynamics, is that actually this is the position vector. So what about, for example, we have a curved path, right? So for example, these are x, y, z, and then we have this path, right? For example, so these are path. Then for example, this point, we take the position vector. So this, for example, is its position from, let's say, times equal to 1 or times equal to 0, and then this will be as it moves from this point to this point, so it will have a different position. So let's say we call this position 1, and then this is the okay, let's say position 1, and then this one is the position 2, right? So recall that, for example, if we take the derivative of position with respect to time, recall in physics that the term is velocity. So v is equal to position. Let's say the position is, we'll use the symbol s, so ds over dt, that is the velocity, right? So actually if we take the derivative, then vector, the velocity is also a vector, so the vector will be tangent, okay, this vector, okay, this vector is tangent to the curve, or path, tangent to the path, and that's what we call as velocity, right? And then if we take another derivative, let's say we differentiate the velocity with respect to time, so we get the acceleration, so from dv over dt, right? So another vector will be formed, and we will discuss the orientation with that acceleration vector in the next topics. So this is the acceleration vector. Okay, so that's the important. So we can also take, for example, we have this. If we try to differentiate these functions, then we can get the velocity at, let's say okay, what's the derivative constant? So it's just like 0, 0, 0, 0. All right, so I'll put here. Is it the same? I don't know. Anyways, okay, I'll see you in the next video. It's already 30 minutes, so I'll see you in the next video. Alright, welcome back to this video. So we will have some examples on how to take the derivatives of some vector valued functions. Okay, so let's take, for example, our vector is equal to, let's say, t squared along the I direction, and then plus t cubed in the j direction, plus sine of t along the k direction. Okay, so by the way, it can also be expressed in terms of this notation. Like, for example, the r is let's say t squared, t cubed, and then sine of t. So it's just the same. So the vectors, it's just simply saying that this vector r has these components: t squared, t cubed, sine t. So along the x direction, along the y, and then along the z direction. So let's calculate the first derivative. Okay, so again, please recall that this vector, this is what we call as the position vector. So if we take the first derivative of the position vector with respect to time, then what we get is the velocity vector. Then if we take the derivative of the velocity with respect to time, then what we get is the acceleration vector. Okay, so basically when we try to take the derivatives, we're just actually taking the derivatives by components. So for example, let's take the derivative of this x component first, and then the second component, and then the third component. Okay, so let's do that. So r prime, okay, so this is the first derivative, is equal to, what's the derivative of t squared? So it's just 2t, and then plus what's the derivative of t cubed? So it's just 3t squared, the j, and then this one would be sine, so it's like cosine t along the k direction. Okay, so if we take another derivative, let's say the second derivative, so what we get is 2i plus 60j plus negative sine t along the k direction. Okay, so this is the acceleration. Okay, let's name this. This is the acceleration, and then this one is the velocity. Okay, example number, let's say this is example 1, and then let's have another example. Okay, example number 2. So we have this vector, or let's say calculate r double prime of 3 where r of t, okay, let's just put it here, r of t is equal to ln t squared. Okay, so it's just another notation. Okay, by the way, I forgot to sign here. Okay, so basically this vector, this position vector, has this component ln of t, and then the function t, and then the function t squared. So we are asked to take to evaluate the second derivative at time is equal to 3. Okay, so to do that, let's first take the first derivative. Okay, so what is the ln of t? It's just basically t to the negative 1. Okay, and then what's the first derivative of t? Is just 1, and then this one is just 2t. Okay, so by the way, I did not write in terms of these Cartesian notations, so it's just the same. Okay, next let's take the derivative again. So we have negative t, okay, and minus 1, so negative 1 minus 1, so minus 2, and then the derivative of a constant is 0, and then the derivative of this one is just 2. Okay, so this is it actually, but then we are asked to evaluate at time is equal to 3. So in this equation, let's substitute all the t with 3. Right, so our prime of 3 is equal to negative, okay, what's this, 3, negative 2, right, 0, 2. Okay, so basically it's just negative 1 over 9, 0, 2. Okay, so to write in, if you want to express that in a Cartesian form, then we can express it as negative 1 over 9, let's say I, and then 0j plus 2k. Right, so that's the answer.